Okay, so you're able to hear me, right? So far we have learned about so many things related to, we studied about statistical parameters. We have learned about probability. We learned about linear algebra, matrices, and we also have studied about dimensionality reduction techniques like PCA, LDA. LDA is not only dimensionality reduction technique, it is also able to categorize the data. We have seen all that stuff, right? So, in one or the other way, we studied about the data, right? We studied the data in higher dimensions. We studied the spread of the data, how to analyze the data, given data, and all that stuff. So that is all about processing the data and understanding the data. That is not actually the machine learning stuff. So we have, they are all directly related to machine learning, but is that is not actual machine learning. So we have also studied about uh, item set mining, which is related to combining the relevant items or relative items in the basket, right? Something like basket analysis. In that, we have learned about a priori algorithm, Eclat algorithm, projection based algorithm, uh, maximal item sets, closed item sets, non-derivable item sets, derivable item sets, and all that stuff. So that is somehow related to the machine learning algorithms. But today we will actually see what is machine learning. Okay, what are the types of machine learnings and what are different things that we do in machine learning. So with that as an intro, let's understand what is machine learning. Machine learning is a subset of artificial intelligence. You know what is a subset? It is a field of artificial intelligence which provides machines the ability to learn automatically and improve from experience without being explicitly programmed. Okay, so to understand this, take the analogy of a child. So a child couldn't actually distinguish different kinds of fruits when he was around like 1 year or 1 year or 2 years, right? So everything looks same to him. He couldn't, or else he will not be able to recognize what is an orange, what is an apple, or whatever it is. Everything is same for him. So as time passes away, as he grows, he will understand, he will gather lots of data, he will understand that data, and as time passes away, he'll be able to distinguish different fruits. He will be able to say what is apple, what is orange, and how does that actually taste, right? So as and when more and more data is being incorporated into his mind, or he injects it into his mind, he will, how does that child gathers the data? Based on the experiences, right? Based on uh, based on his experiences, based on the data that he gathers by roaming around or by talking to someone or by seeing something. He will gather all the data, and that data helps him to actually analyze different fruits, right? And that's how the machines will also learn. As and when we inject more data to the system, what the system will do is it tries to understand the data, it will analyze the data, it gathers key insights from the data, and using that data, it will actually distinguish the outputs, right? In the similar way, here the system or the machine learning algorithm is similar to the brain of the child. So, to the brain of the child, he actually injects the data from the different sources that he experiences around as he grows. Similarly, the algorithm will actually takes the data that is injected to it, and it actually analyzes the data and derives key insights from the data, and using that data that is ingested to it, it will be able to figure out or derive the outputs, or it can actually provide an understanding, provide the required output. That is what machine learning actually do is, what we inject to the algorithm, we inject the data. From that data, it automatically derives the I mean, it automatically understands the data and gives us the output based on the new data that we feed to it. That is what machine learning basically means is. Now, what what are the types of machine learning? So machine learning types are categorized into three types. One is supervised learning, the second type is unsupervised learning, and the third type is reinforcement learning. So let's understand what actually each type of this machine learning means is. Supervised learning is similar to someone supervising you in your learning process. Let's suppose if you are a student, teacher is a supervisor for you. He will give you all the inputs, and based on those inputs, you will actually try to learn the stuff, right? So what does it actually means is, to keep it simple, in supervised learning, you already know the output or the type of output that you will actually have to say. The best example for this is classifying a dog or a cat. Okay. So you classifying a dog or a cat. In this, you know, the output can be a dog or a cat. You will not be having anything apart from this. So when you feed the data to such kind of machine learning type or such type of machine learning algorithms, you not only feed the input data, you'll also feed the output as well. What that actually means is, you already have learned about features and labels in the data matrix, right? Features are the inputs that we feed to the algorithm, and label is the output that the algorithm derives from the features that you have fed. So your data that you are feeding to the machine learning algorithm has both inputs as well as the output, right? Just give me a second. So what I mean to say is that um, the data that you feed to the machine learning algorithm will have both inputs and the output. So inputs are the features and the output is the label. Okay. So that is what. So you're supervising the model and you're also explaining about the output to the model. So in the supervised learning, you not only will have features, okay? So you will not only have features, but you will also have the output. So these are all the features, and this is the output, okay? So when you feed data to this particular machine learning algorithm of type supervised learning, you feed the feature as well as the output to that model, and um, based on the data that you have fed, in future if you are feeding any kind of data, it will be able to derive the output only uh, based on the classes that are there in the output. So these futures are actually whatever futures that can be, whether if you're distinguishing cat and a dog, if you are distinguishing cat and a dog, so these features are different. These features are nothing but the data that is used to distinguish a dog and a cat. It can be a tail size, height of the creature, and weight of the creature, eyes and lens type of lens or something. All of them will be falling under features, and all of these features will be used to derive the output. Now, what are you saying to the algorithm? To the algorithm, you are saying that if you are having these features, and that is dog, and if it has any other different features, it is cat. You're already helping the algorithm to actually know the output. It is not automatically deriving the output. You're also the data itself is telling the telling to the algorithm that for a defined set of features, this is the output. So what is that algorithm actually has to do now? It just has to map the input to the output. That is what that algorithm has to do, because you are feeding the output as well. So to the algorithm, you're giving the input and you're also giving the output. Okay, you're not only giving the input to it. Input is nothing but the features, and output is uh, the label in the data matrix. To the supervised learning algorithms or you're not only giving the inputs, you're also giving the outputs. So what does that? Let's suppose I would say X is the input and Y is the output. What is this algorithm has to do is it has to, build a function such that if you feed X to it, it has to give the output. Output is nothing but the labels in the data matrix. It will be a defined set of values, whether it is dog and cat, 1 or 0, spam or no spam, in case if you're classifying emails. So that is what actually supervised learning means. For the supervised learning, you're also feeding the output to it. That is the major thing that you have to notice. Okay, so what is this algorithms will basically do is it will create a function such that when you feed X to it, the input to it or input feature vector to it, it will actually tell you the output. Output will be a defined set of values, whether it is dog, cat, or whatever it is. A single output basically. It says whether it is a dog, it says if it is a cat or not, something like that. Okay, that is what supervised learning means. Unsupervised learning actually means is that to this unsupervised learning, you will not feed the label or you will not feed the output. What you will just feed is you will just feed the features only. Once the features are fed to this particular algorithm of type unsupervised, uh, what it will do is it will identify the patterns in the data. Okay. The best example for this is, let's suppose if you're feeding a data, something of this sort, which is in tabular format, it will have multiple rows. But the only thing that you have to understand is that it will not have any output label or label given to the algorithm. You will not give the output to the algorithm. What you will just give is you will just give the data to this particular unsupervised learning algorithms. So what these algorithms will do is it will basically group the, you know, it will basically group the data together which are similar. It will group the similar data in the data matrix that you have fed. Okay, let's suppose this particular data has features of dog and cat. Okay, you haven't specified which is related to. Let me mark the data in such a way that you will understand this. So I would say the column number 1 is dog, column number 2 is dog, column number 3 is dog. Okay, and now I have another 3 rows, another 2 rows which belongs to cat. Okay, now in this case, what you're doing is you're not actually giving any output to the algorithm. So, but what this algorithm basically do is 4 and 5 belongs to the cat, 1, 2, 3 belongs to the cat. Now, what these unsupervised learning algorithms basically will do is it groups 1, 2, 3 all the dog related categories into one place. So it will create 2 groups. One group has all the features, or I would call this as cluster or a group. So it will create 2 clusters now. The clusters means the set of points that are similar to each other. So it brings all such kinds of points close to each other and forms a group of points which is called as cluster. So now what these algorithms will basically do is, even though if you're not feeding output to it, based on the data that you're feeding, it will try to figure out this. So it comes out with an output saying that 1, 2, 3 belongs to one type of category and 4 and 5 belongs to the other category. Okay, so that is what gives us the output. It gives us an output to us. It basically understands the data and clusters or groups similar data points together and forms cluster. So that is what unsupervised learning actually means is, for supervised learning, you will supervise that by saying the output, okay, so these are the features that belongs to cat, dog. These are the features that belongs to the cat. So in future, if you're giving something of the, now what this algorithm, based on this data, what this algorithm will actually try to understand, it tries to understand the relation between the inputs and the output. Okay, so that is what this function will be. This function will actually will be derived by the algorithm, such that when you're giving a specific input in the future, it comes out with the output. Okay, so that this is what it actually tries to learn. It tries to derive this function. It tries to derive the relation between the inputs and the output, as both inputs and outputs are fed. So in future, this the task of the supervised learning algorithms is that if you feed an input, it tells you the output. Okay, so that is what supervised learning algorithms will basically do. Unsupervised learning algorithms, basically what they will do is, yeah, for the unsupervised learning algorithms, you will not feed the output. What you only feed is the features. So based on by feeding the features to the unsupervised learning, what that unsupervised learning algorithm will do is that it groups the uh, points which are relevant or which are similar to each other based on different techniques. That anyways we will understand that, but you just have to understand that for unsupervised learnings, you are not feeding the output or the label parameter. What you're just feeding is a feature. Based on the features, it will group the similar points together and forms the clusters. And what is reinforcement learning is, reinforcement learning is nothing but, for this you will not feed any kind of data to it. Okay, you will not feed any kind of data to it. Based on the actions, it will generate the data on itself. The best example for this is, let's suppose you are dropped in an island, in a new island, which you don't have any information on it. Unfortunately, due to some calamity, have you got yourself dropped into an island, so you don't have any information on that. How does the climate will be there, what food will be available there? You don't have any information of that island. So what you will do, as initially you will be in a kind of situation of panic, like, and later what you will start doing, you will try to understand that island. You move in some direction, and if you are seeing some kind of I mean um, some kind of warning over there, or some kind of threat, if you observe some kind of threat over there, you will revert back and go in some other direction, right? If you're finding a good kind of weather over there in towards that direction, you will keep on moving towards that direction. So your actions will tell you, your actions will be your input. And if you're getting a warning, that would be a punishment for you. So it says you that you shouldn't go in that direction. If you are going in such a direction that your weather is comfortable for you, or if you're getting more and more food in that direction, you will keep on going to that, right? That is something called as reward. So based on the rewards and punishments, your input will keep on changing, right? Your direction will keep on changing. So that will be the input. For reinforcement learnings, you will not have any input. Your actions will be your inputs. Based on your punishments or rewards, you will keep moving. Okay, so that is what reinforcement learning is. The best example is the self-driving cars is an example of reinforcement learning. So you're trying to towards that, like, if it finds an obstacle, it will not move in the direction, it changes its direction, right? So that's a punishment. So if you're not seeing any obstacle, that's a reward, so you keep moving in that direction. So self-driving cars is best example of reinforcement learning. Okay, so the one thing, the takeaway from this particular slide is that for supervised learnings, you will feed the inputs as well as the output. So the major role of the algorithm is to map the inputs with the output, so such that in future, if you're giving any input, it using that particular function that it has developed, that is mapping the inputs and the output, it should be able to tell you the output. Okay, For unsupervised learnings, you will not feed the output. What you will just feed is the input features. So based on it, it will try to analyze the data that you have fed, and it comes up with similarities in the data, and it clusters the data similar to each other. Okay. So one such example, you already have seen, right? The items at mining. What does it a priori algorithms, eclat algorithms, what they're all doing, they're actually creating association rules. Association rules means what are the frequent items that happens together, right? So it's grouping the similar items, so that comes under unsupervised learning. Okay, you will see that shortly. So that items at mining or association rule deriving, all of that comes under unsupervised learning. Reinforcement learning means you will not feed any input to that actions of that particular agent or a robot. The person that we are talking in the example that we have just spoke, in that the person is the agent. Okay. And going to some direction is called as an action. And we also already have seen some harm happened with a particular action, we call that as punishment. If some favor happened with a particular action, we call that as reward. Based on the rewards and permissions, that agent actually behaves. Okay. The movement of that agent is the input um, for that particular kind of learning, reinforcement learning. So the best example for that is self-driving cars. Okay. So these are three different types of machine learnings. One is supervised learning, unsupervised learning, and reinforcement learning. Okay, is this clear? Okay,
Yeah,
just this is just the definition. You can just this is what we have discussed. In supervised learning is a method in which we teach the machine using labeled data. What is labeled data? Output is nothing but the labeled data. So based on the features, you are also feeding the output, whether that is dog or cat. Okay, or if you take the email as a consideration, spam or no spam, such kind of we supervised learning is a method in which we teach the machine using labeled data. Okay. In unsupervised learning, yeah, if you want to also take an example, when you are, if you take a child, if you want to say him, if this is the dog, you will show the features to that features of the dog and say this is dog. And you take the cat, you show him the features of the cat, and you also say him this is cat. In future, if once he learned the based on the features and the output that you have taught, when if in future if you are showing him a new dog with a different color or with a different tail size or with different skin tone or whatever it is, still he should be able to figure out that as a dog, because that new dog will not much deviate from the dog that we have shown him when he was actually learning that. So he will be able to figure that as a dog, even if some texture of it or some features of that changed, because it will not quite deviate from the actual learning dog that we have taken, which has using the features that we have made the children learn that. The new dog or the test dog that you have shown him to make sure if he understood the earlier teachings or not. Yeah, when if he's able to figure that out, he's good. Sometimes he may not be able to figure that out. That could be because of the bad way of teaching or the algorithm, or the child would not be able to adequately uh, adopt the teachings that we have given to him. So that's a different case, but that is one of the examples. So we are actually saying the output as well. We are also feeding the label to the algorithm. Such kind of learning is called as supervised learning. And now, in unsupervised learning, what you will do is you will not supervise it. You will not, or that means you're not giving the output to that label, to that algorithm. What you are just giving is you are giving set of data to it. So what that kind of algorithms do, they will group the similar, you know, they will group the similar data points as a cluster. Let's suppose if you, for a person or for a child, I mean, if you are a grown adult, okay, So if you doesn't necessarily need to be taught what is a dog, what is a cat. Even if I, as you're a grown adult, if you're given some set of creatures, you can actually group them what is what. You don't really need to have to be taught what is dog, what is cat. um, so that would be an example. You will not be fed with the, you will not be taught with the outputs, or the output labels will not be fed to the algorithm. Only the data will be fed. What that algorithm will do is it will actually cluster the similar data points in the unsupervised learning. In reinforced learning, an agent interacts with its environment by producing actions and discovers errors or rewards. That we already have taught, have spoken, right? So here, agent is a person on an island. Environment is walking towards different directions, and based on the rewards or errors. So if he's seeing wild animals in one direction, he will not go further in that direction. So that is a punishment. So he has to revert back. And if he's seeing some kind of fruits, fruit trees, or some kind of food, water, fresh water in some direction, that is a reward. So he'll keep moving in that direction. So those will be the inputs for that agent. So those are the terminologies that you have to understand. So these are the definitions for them. And what are the types of problems that for that these different machine learning types will solve. Okay, let's come back to supervised learning. Okay, supervised learning will solve two types of problems. One is regression and the other one is classification. Now let's understand what is the difference between regression and a classification. Okay, classification means if you're given some set of emails, you have to classify which is a spam and which is not a spam. Okay. So that is called as classification. And we also have discussed an example of dog and cat. If you're fed up with some set of data, you should be able to say what is dog and what is cat, right? So that is called classification. Okay, saying differentiating different classes or different creatures, whatever it is. So that is called as classification, differentiating different items. Okay. In regression, the output would be a continuous the continuous variable, or continuous it's a continuous variable. Basically, the output of the regressions would be continuous variable. The best example for that is, if you're given a weight of a person, you have to predict the height of a person, right? Height of a person is a continuous random variable, right? Height can be 5 feet, 5.1 feet, 5.11 feet, 5.12, 5.5, whatever it is. So that is a continuous random variable. So regression algorithms are such a way that they will produce a continuous random variable as an output, not a discrete values. Whereas classification will give you a discrete output, something like 1 0. 1 means spam, 0 means not a spam. 1 means cat, 0 means not a cat. Something like that, or 1 or 2. So classification gives you a discrete output. Regression will actually gives you a continuous random variable as an output. The example for that is predicting the weight of a person given the height of the person. Okay. Such a kind of algorithms are called as so those two comes under those two problem types will be solved by supervised learning. And how do we solve that, what algorithms we will use, we'll all come to that later. But those are the problems that we will try to solve with supervised learning. And coming back to unsupervised learning, as I told you, it cluster the similar data points in the data that you have given. Like if you're fed a data that contains the features of a dog and a cat to that particular unsupervised learning algorithm, it actually clusters all the dogs and it also clusters all the uh, you know, cats. Okay. And if you take the best example, I mean, in the real world example, if you are fed up with if the algorithm is fed with or injected with a data that contains of, you know, customers uh, who has uh, high payout rate and who are not paying back the loan amounts. Okay. So when you fed the data to it, it actually clusters. When you fed 1,000 customers to this particular algorithm, it clusters all the valuable customers into one cluster, and all um, what we call them as uh, or I would say invaluable customers, or customers who don't pay back the loans. Or it will cluster all such kinds of customers into one group, so that you have two groups now. Now you can use the data, the clustered data, to run your business or promote some business ideas to them. So for the best customers, you can give more offers so that they will take more loans, and they will pay the money back for sure. Even though it could be not 100%, at least 99%. And for the other customers, you make sure you are not giving any further loans to them, because they are not paying back to you. So that's how the clustered data can be used. So out of 1,000 customers, if 16%, 600%, I mean 600 customers are doing good, you run the offers only to those 600 customers. For the 400 customers, you make sure no offers have been given to them, or no other loans are sanctioned to them. That's how that clustered data can be used in your analysis. The association is nothing but how frequently the milk is bought when bread is brought. So that is called as an association. You already have learned all the algorithms that are related to association, and it is already done. So that comes under unsupervised learning. Okay. For reinforcement learning, this is an example. So this man has to enter at some place, and he will be able to come out at one place, which is considered as a win. So he goes in a particular direction, and if that is a punishment, he will come back and he will go in the other direction. So if he is not finding out any obstacle in the direction, he'll keep on going in that particular direction. Okay, so for every action that this agent will do, that data will be generated in your matrix. Okay, so those matrices will be used for that by that agent to move in a specific direction. If that uh, if that direction is giving him a punishment, he will use the same matrix to revert back to the original state. Okay, to return back to the original state from where he went forward, in which he got the punishment. So if he is not getting any punishment, he'll keep on moving in that particular direction, and that will be stored in the matrices. And you'll also see different algorithms for every one of these things. But these are the types of problems that these different types of machine algorithms will try to solve. And the type of data, you already have known this. For supervised learning, you're giving the labeled data. That means you're also feeding the output. For unsupervised learning, you're giving unlabeled data. The data will not have any labels. What this will do, it will cluster all the dogs and cats. Okay, it will not say dogs and cats, but the only thing is that it will cluster the similar animals into a group. Okay, if you look at this is the labeled data. You're saying this is cat, this is dog, but in the unlabeled data, you're not labeling anything. What you're doing, you're feeding the data. It is clustering the similar objects into one group. Okay, it is clustering the similar data points. And reinforcement learning, as I said, it doesn't have any predefined data. You will not feed any predefined data to these algorithms. So you will have an agent, it performs an action, and if it is an reward, it will keep on it. If it is a reward, it comes back and it performs that action again. So if it is not a reward, if it's a punishment, it goes back to the own state and the old state, and it will perform the action again. Okay, the other kind of action. So that is what reinforcement learning actually will do is. So training. So you will have an external supervisor. That means you are training the algorithm with the output labels. You are specifically training with the output label so that it will be able to predict. It will not have any supervision. You have to learn on your own. Okay. So here you will have a teacher, which is labeled data. That's an supervisor. No supervisor means you have to learn on your own. And the reinforcement learning is also no supervision. None of them will teach you. Okay, you have to learn on your own. And then these are some of the examples. So what this will do, forecast outcomes. As I told you, we're predicting the weight of a person based on the height of a person, or predicting height of a person based on the weight. Forecasting the data, classifying the data, all comes under supervised learning. Unsupervised learning means discovering the underlying patterns. I mean, clustering the similar data points and all that stuff is unsupervised learning. Reinforcement learning means experiment based on the rewards, move forward. That is learn series of actions. So that is the aim of them. So the approach, we already have discussed all of this, but these were kept in different slides. If you look at supervised learning, map labeled input to known output. You will have a labeled input and you're training the algorithm using those labeled inputs, and then you're getting an output which is known to you, right? Because you already have fed the outputs based on the set of the outputs that you have fed. You will get one output in future based on the test data that you will feed. Okay. In unsupervised learning, you will feed unlabeled data. What that algorithm will do, it explore patterns in the data and it will feed that output. Reinforcement learning is like trial and error. Do a trial. If that is success, go forward. If it is an error, come back and do in the other way. Okay. So that is what it is. Um, in supervised learning, you will have a direct feedback. You have known output and you will have a feedback. Unlabeled, no feedback. In reinforcement learning, reward system. So if it is a punishment or reward, based on that, the input state will depend for the next step. Okay. So this is the output feedback system. So the applications, as I told you, for supervised learnings, we do forecast sales, risk evaluation. Risk evaluation comes under that, right? We were discussing about the application. The credit scores of different customers. It groups all the customers with good credit score, and it groups customers with bad credit score. So you there you can do a risk analysis and you offer more offers for customers with good credit scores, and don't offer any further loans or privileges to the low customers with low credit scores. So that is what risk analysis is. Forecast sales. So forecasting sales means, like, let's suppose if you have the data that forecast sales in different months of the previous years, and now you can forecast the sales in the based on the old data in the for the next financial year. You can derive that using supervised learnings. Unsupervised learning means recommendation systems. Recommendation system means if you have some set of movies, okay, and now uh, if you have different customers, you can group all the customers who are watching similar movies, and you can recommend the same kind of movies to those set of customers. Okay, so that is a supervised learning. You're not feeding any output to it. Self-driving cars is an example of reinforcement learning. Okay, so these are the different things um, that we have shown, that are different types of machine learning types that we do have. Now look at these problem statements and let me know what kind of learning is that. So the first problem statement says study a bank credit data set and make a decision about whether to approve the loan of the application based on his profile. Study a bank credit data set and make a decision about whether to approve the loan of an applicant based on his profile.
Labeled data set.
Supervisor.
Supervised.
Why?
Supervised.
Because
It has
there is
input and
already a
output.
data, right? Credit data set is there. So there is a known data set. So that's why it's a supervised learning.
Okay. So to establish a mathematical equation for distance as a function of speed, so you can use it to predict distance when only the speed of the car is known. What is that? This is supervised. To establish a mathematical equation for distance as a function of speed.
Supervised.
Why?
Because
With the help of mathematical equation, the speed
Yeah.
will be maybe decrease.
Distance can be found as a function of speed. So speed will be the input, and then using this function, you are deriving the output. So this is supervised. So when you're deciding anything, if you're predicting a single output, all of them comes under supervised learnings. So giving, if you're able to decide whether you have to give the loan or not, it is binary, right? 1 or 0. You're predicting an output, single output. You're not clustering the things. Okay. So it's predicting the speed, which would be in continuous random variable. So does this fall under regression or classification? This falls under regression or classification.
Classification.
Speed of a car based on the distance.
Regression.
Oh, okay, regulation. Sorry.
So yeah, regression means the difference between classification and regression is classification will say yes or no, right? Spam or no spam, dog or cat, right? It just classifies. Regression means it will the output would be a continuous random variable. The output of a classification is discrete term. It will be a discrete value. So this falls under regression. What about this, the above one?
Classification.
Classification.
Yeah, this is
Class.
classification. What you're
Classification.
classifying, whether whether to approve the loan or not.
A prawn not.
Okay? Approve the loan or not, don't approve the loan. So that's a classification. What about this? To cluster a set of movies as either good or average based on the social media outreach.
Unsupervised.
This is
Unsupervised.
unsupervised because you're clustering the
Only
data.
good or bad.
What about this? To perform market basket analysis by finding association between items bought at the grocery store.
Unsupervised.
Yeah, this is also unsupervised. Association is something that we have seen as unsupervised, right? So you're associating the items in a in a market analysis. What are the association algorithms that we have seen? Have you remembered that a priori algorithm, eclat algorithm, projection based algorithm? So those are the algorithms that we have learned to derive the association rules, right? Based on the frequent item sets. I think many of you haven't seen that video set, I think. And what about this? The last one, place an agent in any one of the rooms, and the goal is to reach outside the building 5. So place an agent in any one of the rooms, and his goal is to reach out of room number 5. What is this?
And
What's that? What type of machine learning is that?
Reinforcement learning.
Yeah, this is
Reinforced.
reinforcement learning. No input is fed reinforcement. No input is fed to this. Okay. So this is all about the intro to the machine learning. Now let's understand this important concept, which is very important to understand. What Whether the machine learning algorithm is doing good or not. This is called as bias and variance trade-off. Okay. So the first thing is you have to understand what is bias, and you also have to understand what is variance. Do you know what is variance? What is variance?
Spread of data.
Yeah, the spread of data from the mean is called as variance, right? That is in terms of statistical view. When you're analyzing the data, that is the abbreviation for variance. How how spread, I mean, how far the data is spread from the mean is what variance actually tells you. But in machine learning lingo, it is slightly different, but it conveys the same meaning. We will actually try to learn that bias, I mean variance, and we'll also try to learn bias. Okay, so let's understand what does bias and variance trade-off actually means is, and you also will understand what is bias and variance. Now you are given with some data. Okay, so let's suppose these are the heights and weights of different persons in your data. Okay, different persons, that is your data. And now the if you want to represent this data, the best line, the best curve that represents this data is this is the curve. So how do you understand this data? If the weight is less, the height would be less. And at some point, as the weight is keep on increasing, the height is also increasing. But at one point, at a specific height, at a specific weight, the height is remaining constant, right? It's not growing in a linear fashion when you compare with the heights that are coming up before this. After this, what is this happening? The height is remaining constant. The persons are becoming more and more obese, right? They're becoming fat, but the height is not increasing. Okay, that is what the data that is given to you. Now, if you want to represent this data with a good line or with a good function, this is the function for it. This line is something which is representing that in a good way, right? So this curve can be represented with a function. Let's suppose I would say with a with a polynomial function like x square plus 2x plus 3, something of the sort, of order 2. Okay, so this is the best curve that is representing this data. Okay, but not every algorithm will give the best curve, right? So every algorithm will predict different, it will not be optimal all the times. It Different algorithms will give different curves when you feed the data to it. Okay, so this curve is something that is being given by the machine learning algorithm. Um, to keep it short and to make you understand better, let me take another example. Let's suppose I have this particular data with me. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, so this is my data. Okay, so this is my data. Now I got few points in my data set that is given to me. I got few data points. I would represent it this way. Okay, so now I got few points. This is 1 point, this is 1 point, this is 1 point, this is 1 point. So these are my data points. Somewhere this. Okay, let's suppose these are my data points. If I want to represent this, when I fed this data to my machine learning algorithm, so this is my input X, and this, it should tell me the output. Okay, so these are the weights and heights. Sorry, these are weights and heights of different portions. Again, I would say weights and heights. Now, when you feed this data, what this algorithm basically will do is it will try to map the output with the input. What is the input here? Weight is the input. What is the output here? Height is the output. And if I construct a function for this particular data points, what this algorithm will try to do is it comes up with a mapping for the input to the output. Okay, it tries to map the input to the output. Okay, it comes up with a function. What that function basically could be, y is equal to x plus 2 maybe. Okay, so this is the function which will be found out by the, or which will be derived by this machine learning algorithm. Okay, it is just trying to map the input with the output. Okay, it is trying to map the input with the output. Now in future, if now the maximum value here is just like 4.5 or something, right? In future, if you're given with something, if the input something like 10, if the weight is given as 10, it will tell you 10 plus 2, which is 12 centimeters or meters or whatever it is. So this machine learning algorithm will try to understand this data, and it maps the input with the output and comes up with a function. And this is that function. And whenever you are getting a new input, it just applies that input to the that particular function, and it throws out the output, which is 12. Okay. So that is how the algorithms will actually map the inputs with the output. What kind of learning is this? Is this supervised or unsupervised?
Supervised.
This is supervised because you're already feeding the output to the data, and it is just coming up with the function. Okay. Now, such similar kind of function is this. Okay. X square plus 2x plus 3. This is not a straight line. If this is a straight line, we can represent with x plus 2. If it is a curve, it has to be a polynomial function with x square plus 2x, something of that sort. Okay. All curves will have higher polynomials. Okay. Now, the best ideal algorithm or the best algorithm will actually comes up with such kind of curve. Okay. And now, let's keep that aside. Now, what I'm trying to do is, in this data that is given to us, we have to split the data. We cannot use all the data to train the model. Okay. We need some data to actually test the model as well, whether how the model is actually working. We already have discussed what is the testing, what is the training set, and what is the test set, right? I think we have discussed in our initial days. So not all the data will be used as a training data. We have to split that as 70% or 30%, and 70% of the data is called as training set, and that training set will be used to train the model. Okay. And then the remaining 30% of the data will be used to test the model. And as we already know the output for those models, what we just will do is compare the output given by the model with the known output, and we calculate the accuracy of the model. Okay. We already have discussed that. So now we have split the entire data into training set and test set. So the blue dot denotes the training set and the green dots denote the test set. When we are training the model, we will not feed the test data to that model. We only feed training data to that model. Now we got only the training set uh, fed to the model. Now let's go back and let's understand. Now I have taken the first algorithm. We have different machine learning algorithms available for us, which we will discuss later. The best algorithms that are available for different actions or for different types of learnings. Okay, but now let's not go further for what kind of machine learnings that we will feed and all. Let's suppose there is a machine learning algorithm, and we have given this data, the testing data, to that particular model. And now what that model has done is it constructed it find out the relationship between those data points given, and it came up with this particular line. Okay, what line it has came up with? It came up with a straight line, right? This is the straight line it come up with. Now what this algorithm says is that this is the best line that describes the data that is given to you. Okay. And now you can clearly understand that it quite deviated from the optimal line, right, which actually represents the data. So this is the optimal line. This is the optimal line. This is the predicted line by the algorithm that we have chosen. Okay. So this is the optimal, means it captures the true relation between the height and weight. Okay. It captures the true relation between the height and weight. Whereas this is the predicted relation between height and weight by the algorithm that we have chosen. And now what is bias basically means the inability of the machine learning method to capture the true relation is called as bias. Okay. So there is a deviation, right? This is called as bias. So inability of the machine learning algorithm to capture the true relation. Okay. So it didn't capture the true relation. It deviated from it. That is called as bias. Okay. So this is what I was saying. The straight line will never capture the true relation between the weight and height, no matter how well we fit it in the training set. So a straight line cannot represent this data, right? Whatever data that is, this can be, if you choose that as a straight line, or this as a straight line, this as a straight line, any straight line cannot actually fit the training set that we have taken. Only line, or it should be a curve, and that curve should look something like this. Only this curve will have the capability to actually find out the true relation between the height and weight. But what is bias? Bias is the incapability of the machine learning method to capture the true relation uh, between the inputs that we are given. Okay, true relation between the variables or something. So this difference is called as the bias. So now, if you look at this, there is a high bias, right? So this particular algorithm has high bias. So this is the expected, and this is a straight line. There is a lot of difference, right? There, it's not even coming like a curve. There is such kind of models are called. I mean, this particular algorithm is said to have high bias, a large amount of bias. It is not at all capturing the true relation between the height and weight. Now, if you go back to the next slide, you will understand the actual meaning of bias much better. Let's suppose these are the data points, okay? Now, this is the optimal line we were talking about. But if you're feeding these data points to a model such that that model gave you this particular line. Okay, this is the line, that particular model, the second machine learning model gave you this particular line. What this particular line is doing, it actually capturing the actual relation, the exact relation between the height and weight. It actually joined all the points, okay, all the training points. Okay, in this case, I say the bias as 0. Okay, because this squiggly line can handle the arc in the true relation between the weight and height. It has very little bias. Okay, it actually captured the exact relation between the height and weight for each of the data point that you have given. Okay, this can be something like a degree of 10, something like a polynomial of degree 10, x to the power of 10 plus x to the power of 9 plus x, or something. Whatever the polynomial equation that is, in this case, it is um, weight to the power of 10 plus weight to the power of 9 plus weight, something of that sort, where x is nothing but height. So what this algorithm has actually done, it has joined all the data points exactly, and it came up with a curve something like this. Okay, so in this case, we would say there is no difference between, I mean, this particular model has exactly captured the relation between the height and weight, right? There is no difference. Even this has some bias, as it captured the relation but not the exact relation. Okay, this is better when compared to the straight line, and this is an ideal case. Okay, this curve is an ideal case. Nothing can replace, no other curves can replace this data, can better represent this data. This is the best curve that represents the data. So this is called as, this particular curve is said to have bias 0. Okay, and now compared to this, you will understand, right? So this has higher bias when compared to this. Let's suppose the bias for this is set to have 100, and the bias for this is set to have 50. And now if you take this particular curve, the bias for this is set to have 0. Bias is nothing but the quantity that specifies the how much the algorithm has captured the relation between the input and the output. Okay, so now that is what bias means. Did you understand what actually a bias means?
I have a little confusion.
Yes.
Okay. Uh, Bias is nothing but, just understand this. Bias is how well we capture the relation between the input and the output. Okay. So that is what bias actually means is. So if you actually look at this particular data, you have two models, machine learning model 1 and machine learning model 2. And now you fed the training data to the model 1. Model 1 came up with a representation of this data with a line, with a straight line. Okay. Now, do you think this straight line actually captures the relation between height and weight for this particular data set? No, right? Let's suppose if you have taken a weight, if you take the same graph, now if you want to calculate the height of a particular person at this point, this particular straight line gave the right value for this particular point. Now, if you take a point at this place, like if you take weight, if you are trying to calculate the weight, height of a person with weight, something like 100, it is giving a value somewhere around, you know, like 6 feet or something. But it is far away from the line, right? This is 4 feet. Let's suppose this is 4 feet. Okay, this is 6 feet. This 4 feet is much lesser than 6 feet. This is the actual weight of the person with weight 100 kgs. But your algorithm predicted line is giving us 6 feet, which is false. Okay, if you look at this, there is a 2 feet difference in the output given. It is not actually capturing the true relationship. Okay, this is the output of algorithm 1. Okay, I am saying this curve is an optimal uh, optimal solution. Okay, if you this curve will keep on going like this, and now if you take the same 100 kg weight, it is giving you the 4 feet height. Okay, now here let's suppose the actual weight of the person is 4. This curve may give you 4.5 feet or something. Okay, there is a difference of 0.5 feet given by the optimal line. Okay, the optimal line can be given by the second algorithm or something. Okay, now what I'm saying is bias is a quantity that measures how well the relation between the variables are captured. Okay, in this case the bias is high. This straight line definitely didn't capture the true relationship, so the bias will be high in that case. This curve thrown us a difference of just 0.5 feet, which is much lesser than 2 feet. It's just 25 percentage of that 100 percentage of bias given for us. So the bias of this curve is less than this. Okay, is that clear? Let's suppose this is the output of machine learning algorithm 1. This is the output of machine learning algorithm 2. Okay, now machine learning algorithm 2 captured the true relationship between height and weight much better than machine learning algorithm 1. Okay, in other words, the bias of machine learning algorithm 1 is greater than machine learning algorithm 2 because it didn't capture the true relationship between the height and weight when compared to machine learning algorithm 2. Now, if you go back to other machine learning algorithm, it the third machine algorithm actually has given you a curve, has given you this curve. This can be represented with a polynomial equation. Now, if you want to calculate the weight of a person for a particular height, okay, it is giving the exact value that is expected. Okay, it is giving the 4 feet only. Okay, for 100 kgs weight, person with 100 kgs weight, this particular curve, the third algorithm curve, which is capturing the true relation between the data, give you the exact height, which is 4 feet. So in this case, the bias is 0 because it captured the true relation between the height and weight. So now if I keep all the three into one diagram, this line produced by machine learning algorithm 1, this line is given by machine learning algorithm 2, and this line is given by this dotted line is given by machine learning algorithm 3. Machine learning algorithm 3 captured the true relation between the height and weight in the data, right? In machine learning algorithm 2 captured true relationship, but not better than machine learning algorithm 3. Machine learning algorithm 1 captured the true relation, captured the relationship between the height and weight, but much worse than machine learning algorithm 2 and 3. So that's the reason bias for this is higher than this. For machine learning algorithm is higher than this. So bias is greater than for this, greater for this. So bias is just nothing but the a quantity that measures the true relationship, how well the algorithm captured the true relationship between the um, dimensions that are given or parameters that are given. Understood?
Yeah.
Okay. So that is a measure of in the context to whether now we are trying to see. Now I have kept both of the diagrams with their expected outputs into one diagram. Okay. Now this is machine learning algorithm 1 and this is machine learning algorithm 2. And now if you look at the sum of square distances, which is a measure of, you know, uh, this is okay. Now if you look, if you keep both the this is the output of machine learning algorithm and this is the output of machine learning algorithm 2. Okay, let me, this is machine learning algorithm 1 and machine learning algorithm 2. Sum of square distances. Okay, you already have learned about sum of square distances in principal component analysis. Does the best line that is fitting the data will have less sum of square distances or high sum of square distances? Now let me know what is the, whether for diagram 1 or diagram 2 we have highest sum of square distances. Sum of square distances is nothing but, what does that mean? So this square of these distances, right? Let's suppose if this is x1, this is x2, this is 0 because it lied on it, it is on the line, this is on the line. Let's suppose this is x3, x4, x5. So this is nothing but x1 square plus x2 square plus x3 square plus x4 plus square, x4 square plus x5 square. That is the sum of square distances. Let's suppose if all these points are on the same line, it would be 0, right? For this particular line, which is the output of a machine learning algorithm 2, sum of square distances is 0, right? Sum of square distances is actually 0 because it there is no distance between the line and the point. The every point is lying on the line, so the distance from the line to the point is 0. So sum of square distances will be equal to 0. Whereas in the first prediction, the sum of square distances is high. So this is on the training set. Okay. When this line, what I'm representing as the output line given by the algorithm is on training set. Now we are going back to the, based on the sum of square distances, we are saying that this particular line has highest sum of squares. That means it is not representing the data in a right way. Whereas in this case, the sum of square distances is 0. That means it is representing the data exactly. Okay, that is what it means is. Now if we go back to the next slide, now the same lines are applied on the testing set. Okay, now we removed the training sets and we came back with the testing sets. Now if we calculate the sum of square distances for the testing points, sum of squared errors is less for this and more for the squiggle line. So sum of square distance is less now for the straight line and sum of square distances is more for the squiggle line. Okay, that means this squiggle line is working perfectly for the testing set but not the training set. For the training set, it is giving more errors, whereas the machine learning algorithm on the training set is giving less errors. Okay. So even though squiggle line did a great job fitting the training set, it did a terrible job fitting the testing set. Okay. So it this particular squiggle line or the machine learning algorithm that we have used performed perfectly on the training set, but when it came to testing set, it is performing terribly. Now here comes the variance. In machine learning, variance refers to how much a model performance differs between the training and the testing set. Okay, variance is nothing but how much the model performance differs from the training set to the testing set. In training set, if it found out all the outputs correctly, but in the testing set it doesn't correctly find out the output for even for 1 point, we call the variance is high. Variance actually measures how well the model, how much a model performance differed from training set to the test set. Here, in this case, it couldn't able to find out the exact value for even 1 point. Okay, if you look at this output, it found out the exact values for 2 points. Both of these points lie on the line, whereas other points they are far away from the line. But if you take this particular case, it couldn't able to find out the exact output for even 1 point. Okay, but it found out the exact output for every training set. So this says the model performance differed widely in this case. Okay, so the variance is high in this case, whereas the variance is less in this case. Whereas if you look at this, we heard about this bias is more for this, right? Because it didn't capture the true relationship between the input and the output. Bias is more, but variance is less because the performance on the test data is much better. In this case, variance is less. We are not quantifying what we are saying. We are comparing these two diagrams. Okay, based on that, I'm saying the variance is less. Here, the bias is zero almost because it captured the true relationship between the input and output on the training set, whereas variance is high in this case. Variance is very high because the performance of this model on the training set differed completely from on the testing set differed completely from the training set. Okay, so the variance is high for the squiggle line because it couldn't able to find out the exact value for none of the test data, but for training data it captured the exact value for almost all the points. Whereas for the first training model, for the first machine learning algorithm, bias is more because it didn't capture the true relationship between the output and output, because sum of squared errors is higher in this case. Sum of squared error is high. With sum of squared errors, we can say it didn't capture the exact relation between the input and output because most of the points deviated. But it performed the same way on the testing set as well. Some of the values falling on that line itself. So at least for few inputs, for few test points, we are capturing the right outputs. Okay. So this is what you have to understand. Bias is more for this and variance is less, and bias is zero for this and variance is high. Now comes this particular part. The squiggle line has low bias because it captured the exact relationship between the input and output, since it is fixable and adapt to the curve in the relationship between it and curve. But the squiggly line has highest variability because it results in vastly different sum of squares for different data sets. Because it results in vastly different sum of square errors for different data sets. So that means none of the points are on the line, right? So the sum of squared errors will anyways increase. If you have some points on the line, the sum of squared errors for these is zero. So sum of squared errors would be less when compared to this case because none of the points are lying on the line. So every point will contribute to the sum of squared errors. Okay, that's the reason variance is high. In other words, it is hard to predict how well the squiggle line will perform with future data sets. It might do well in sometimes and other times it might not. It might do terribly. Okay, in future data sets, this will never give, there is no hope that it will give you the right outputs. Whereas we have some hope for this particular line. We have some hope because some of the points are at least staying on the line. So we can say that at least for some inputs, for some test inputs or future inputs that we want to predict, it may give you the right output. But this squiggle line will never give you we cannot actually say with higher confidence, or we don't have any prediction on the output of this squiggle line for the future test data or the points that we want to predict. So that is what basically we came up with. In other words, it's hard to predict how well the squiggle line will perform with future data sets. Okay, because the variance is becoming high. It is not able to predict any exact output for the test data. So the model is not performing well with the squiggle output, but it is performing well on the testing data. It exactly captured the relationship between the points. Okay, so that is what you have to understand. Straight line, as I was saying, straight line has low variance because the output has not deviated much on the testing data set. That's right. Variance, basically what it measures, how the change of the performance of the model from the training set to the test set. But here this particular line is performing similarly on the training set as well as on the test set. So we say relatively low variance when compared to the squiggle line, because the sum of squared errors are very similar for different data sets. Okay, sum of squared errors is almost similar for this training set and the test set, right? That is why we say the variance is low. But in case of this particular squiggle line, sum of squared errors is very high in this, and the sum of squared errors is 0. So the variance is so much high in this particular case. In contrast, sorry. In contrast, the slight line has relatively higher bias. Okay, since it cannot capture the curve in the relationship between the weight and height, the bias is high and the variance is low. In other words, the straight line might only give good predictions and not great predictions. It can predict, but it will not give great predictions. But they will be consistently good predictions. Okay, we have some hope here, but here there is no hope because it didn't perform um, at least well on one of the data points, or one of the test points. It didn't perform well on at least one of the test points. So we cannot actually say it will do good on any of the future data points that we want to predict. In case it might do terribly because sum of squared errors is very high. So the few things that you have observed so far is that uh, this comes to an important one. So now we are discussing all this just to understand this underfitting, overfitting. Now coming back here, because the squiggly line fits the training set really well, but not the testing set, we say the squiggly line is overfit. Overfit means you're trying to find out a function that is exactly joining all the points in the training set, which shouldn't be done ever. We actually try to find out the trend in the input that is given to you. That is how you have to design your model. If you're designing your model more focusingly to join all your data points, it happens because of multiple reasons. It could be because of your data not cleaned well. We haven't seen that pre-processing steps, but you have to pre-process your data before feeding to any of the model. That means you have to remove your outliers. We already have discussed about outliers, right? The points which are extreme. We already have discussed an example. The heart rate of the average people in the younger generations would be somewhere around 72 to 80, right? But if you have a person in the same data set with ACE 100, but still his heart rate is 72, it's an outlier. You should get rid of such kind of outliers. There are different methods to get rid of the outliers. So if you're not doing that, what happens is you're considering every point which will corrupt the output in the future. Let's suppose if you're also considering that outlier, what happens if you're getting an input of ACE 98, there is a high chances that you will show the uh, you know the heart rate of that but is with 92 also as 72, because you are considering the outlier of 100, which is whose heart rate is 72, which happens in the rare cases. So if you are actually considering the outliers, or if you're not cleaning the data well, and if you're trying to find out, instead of trying to find out the or predict the trend in the points, if you're trying to find out the exact polynomial function that is joining all the points, if you're trying to make the model more complex so that it actually tries to capture every trend in the data, it will not predict well on the output on the test data. So you want to make sure you have to come up with an optimal thing, a sweet spot, something like this. So what a good model. Now you have seen a simple model, like, okay, So let's come by side. Here, the squiggle line couldn't able to perform well on the testing set, but it performed very well on the training set because you tried to create a complex model such that it joined all the points in the training set. That is not doing well on the testing set. That is one point. In machine learning, the algorithm has low bias and accurately model the true relationship. So for a true model, how does that it look like? It should have high bias or low bias. So the overfitting has low variance or high variance. This has low bias, right? Because sum of squared errors is 0. And this has low bias and low variability. Oh, sorry. Now tell me this has high bias or low bias. The model on the right side, this has high bias or low bias.
No bias.
Low bias. What is bias? Bias basically means how well the model captured the relationship between the input and output, right?
Input and output. Yeah.
So this hasn't captured the true relation between input and output. So this has high bias. When compared to this has high bias or low bias. This has zero bias. This has low bias. And what about variability? This has high variability. What is variability? Variability means how much the output deviated from the testing data to the training data, right? Or training data to the test data. So the output of the test data deviated completely here in this particular squiggle line, right? Whereas if you consider this particular diagram, this has variability very much lesser than the overfitting. I would say variability is variability. Let's suppose for this it is low variability. This has medium variability. That means a right model will have low bias and low variability. Okay, you have to choose a point between these two models. You don't want a model to be overfitting. Overfitting means it captures every trend in the data. Underfitting means it will not consider. It's a simple model. It will not capture the right trend in the data, right? So underfitting has high bias. Overfitting has zero bias almost. Overfitting has high variability. Underfitting has medium variability. You have to choose the bias which is in between both of them, and you also have to choose the variability which is in between both of them. Okay. So such a model would be the right fit. If you look at this, variability is less because the output didn't deviated much. The sum of squared errors is not much when compared from the testing data to the training data. Okay. And also bias is also low because it captured the right trend in the data. Okay. Um, Understood. So that is what overfitting, underfitting, and right fit means. Overfitting means it considers every point in the data, every it will take every change in the data, or every what we say, every angle in the data. It tries to capture every angle in the data, and it capture. I mean, it joins all the points in the training test set. So it may perform well on the testing set, but it will not perform well on the training. I mean, it may perform well on the training data set, but it will not perform well in the on the test data set. Whereas underfitting means, underfitting means it will not capture the trends in the data, completely capture the trends in the data. It would be a simple model. It may predict some outputs in the data, but it will not perform up to the expectations. Whereas when you choose a model which is in between both of them, you will be able to actually capture the right outputs, or outputs which are close to the actual outputs for the given data points. That is what overfitting, underfitting, and right fit means. That is called bias and variance trade-off. You trade-off means you need to make sure the value of the bias and the variability is lying between overfitting and underfitting for the model which has right fit. You should not overfit the model, or you should not underfit the model. You need to make sure the bias and the variability of that particular model is in between the underfitting and overfitting. That is what. So you don't want high variability and low bias, and you don't want higher bias and low variability. You need to make sure they both are in sync, such that you will get the right model. Okay, they both will be in sync already. That's what trade-off basically means is. You understood this or not?
Yes, understood.
Okay. So it's just like, again, I'm just repeating, bias means how well we are capturing the relationship between the dimensions in the data. Okay. The squiggle line captured the exact relationship between the dimensions in the data, which is height and weight. But even though it predicted the right heights for the given weight on the training set, the squiggle line didn't perform well on the test data. So that is called as overfitting. Overfitting means you're considering every point, you're giving the priority for every point in the data. If your data has outliers, anyways, yeah, the example that we have discussed, the 100 years person having heart rate as 72 is a rare case. So you should clean such kind of data. If you consider every data, it will definitely do not perform well on the test data, because in test data, if you have a person with age 98 years and his heart rate is around 100, but your model will show somewhere around 76 or 78, because you have considered a point of 100 years age and 72 heart rate. So that is called as overfitting. And underfitting means you haven't captured the true relationship between the output and output. You captured something but not up to the mark, right? So such kind of relations, if you're not able to capture the true relationship between the input and output, the bias will be high. But for the squiggle line, the bias is zero, because you captured the exact relationship between the input and output. But variability means how much the output changed from the testing data to the training data set, right? So that is what variability means is. Okay. So that variability is higher for squiggle line, whereas it is lower when compared to the squiggle line for the straight line. So the straight line is when you don't capture the right relationship between the input and output, that is called as underfitting, and we call it as simple model. Overfitting is a complex model. You considered everything in the data, and you try to join, you come up with a function with higher degrees of polynomial, such that it has so many curves that actually captured that actually has gone over every point. And that kind of model is called as complex models, and they will be overfitting. You don't want overfitting or underfitting. You want something which is in between both of them. So overfitting and underfitting will be decided by the variability and bias, so that you need to trade off in between both of them, such that you are getting a right model, or a right function that predicts the outputs. So that is called as right fit. That is the difference between underfitting, overfitting, and the right fit. Okay. Now, as we have learned so many things so far, we have learned different types of machine learning machine learning types, which is supervised, unsupervised, reinforcement. And we also have seen what is overfitting and underfitting, and what is the right fit, bias and variance trade-off. Now this is the first supervised learning that we are trying to learn. Classification is a supervised machine learning method, because in classification we also feed the output to the model. If you take this example here, if you take the example here, this is an email spam detector. Okay, you trained this classification model with, you trained this classification model with, you know, um, the training and validation data. So you have taken some set of messages in your data and you mark them as training set and you classified this model. And in future, if you're giving any message to this particular model, it should be capable to distinguish whether that is a spam or inbox. If it is not a spam, it should redirect that particular message to your inbox. And if it is a spam, it should redirect that to your spam email box or spam box. Okay. So this is a simple example for classification. So it is classifying whether the given email is spam or not. Classification is a supervised machine learning method, and you know why it is called as supervised now, where the model tries to predict the correct label of a given input data. So it is trying to predict the label. What is the label? Label is nothing but the output. Output, what is output? Output is nothing but spam or no spam, right? In classification, the model is fully trained using the training data, and then it is evaluated on the test data before being used to perform prediction on new unseen data. Okay, here you are seeing three words. One is training data, other one is test data, and the third one is new unseen data. Why we are developing this model? Now, let's understand this. Okay, let me come up with an example to better explain this. So you have, again, I'm taking the same example, which would be a regression case. um, let's take this example. You have a test data, something like this, right? Let's suppose if you have 100 records in this particular data matrix, that you have 100 records in this data set. Now in this 100 records, what you are doing is you're creating a training set and a test set. So you're creating 80 records for training and 20 records for test set. Okay, this is for training and this is for test. Okay, now you got 100 data records, and now you have 80 trainings and 20 as test data. Now your problem statement says that given an image, you have to detect whether that is dog or cat. Your problem statement is you have to distinguish given image is dog or not a dog, or simply dog or cat. You can say, for now you can say whether that is dog or not dog. Okay, now you are given with, you know, different features of the dog. You have taken 100 different dogs and you have taken different dimensions of the data. And again, I am saying this is like tail length. This is like tail length, or whatever it is, like color of the dog, eyes, number of legs. These are all features. Okay, now your problem statement says when you are given with a new image, you have to say whether that is dog or not a dog. Okay, now you have 100 different dogs data with you with different features, and now you have a label placed also here. Okay, you also have label placed, which is dog. Now you also have a label given along with this, which is label says this is dog. Dog, this is dog, everything is dog. Dog. And you also have taken some random samples which are related to not dogs. Okay, this is not a dog, this is not a dog, something like this. So now you take a mix of the dogs and not dogs for training, and mix of dogs and not dogs for testing. Now you created a model using this training data set. Now you fed this training data set to a model, and this model came up with a function to say whether that is a dog or not. So x is each record that is fed to this model, so that it is coming with the y has only two values, which is dog or no dog. Only two values that are possible for y. Okay, now training is done. Training is completed using this data. Now you have 20 test records, and you also know the output for those 20 dogs, right? You also know which is a dog and which is not a dog. Let's suppose this is the test data. For this test data, when you're feeding this data to this model, you will not pass the label to this. Okay, you will not give label, will not be fed to the data. Only the features will be fed to the model for the test data. Now when you fed this 20 dogs to this particular model, it came up with some set of outputs, right? It came up with an output vector, I would say. This output vector says, I call this as y, which is output. Y dash is the output from the model. Y dash is the output from the model, and y is the actual output. Okay, y is the actual output and y dash is the output from the model. Now the actual output is this. Okay, the actual output actually looks like this. The actual output looks like this. This is dog. This is dog. This is no dog. This is dog. This is no dog. This is no dog. And this is the actual output. Let's say for the 20 dogs, this is the actual output. Now the output from the model is something like this: not dog, dog, not dog, not dog, not dog, dog. So now, how is this model performing? The model performance will be determined by these differences. What is the difference here? So if you look at this difference, if you look at this particular output, so this is a wrong output, right? This is a right output, wrong output, right output, wrong output. So let's suppose, out of 20 findings, if it has find out 17 correct, okay, so this is one of the performance metrics of the model. So if it is finding 17 outputs correctly, and out of 20 inputs that we're giving, then this model is working fine, so that this model is ready for using in the real environment. Now we trained this model with 80 records, tested that, and you also found the accuracy as very good. Now you are going to start this model for the unseen data. Unseen data means you also don't know the output. For the test data, you know the output, and you're comparing that output with the model's output. But for the new unseen data, you don't know the output. You will rely on the output given by this model. And okay, so using that model output, you will actually try to whatever it is, whatever you want to do, you will rely on the output of the data. You blindly believe the output of the model for the unseen data once the model is deployed and being used for different analysis or for different usages. Now once the model is deployed, once the model is tested and deployed, now the unseen data is coming. For this unseen data, you don't know the output. Also for the test data, you know the output, but for the unseen data, you don't know the output, and the model will give you an output, and based on that output, you will actually do the things that are required to be done. So that is how actually every training, testing, and using that model works. Okay, so now if you go back here and see what this is, classification is a supervised machine learning method where the model tries to predict the correct label for a given input data. In the classification, the model is fully trained using the training data, and then it is evaluated on the test data before being used to perform prediction on new unseen data. Okay, first trained and then tested using test data, and then used on the new real data. Okay, so classification is just nothing but saying this email spam or not spam. There are different types of classifications. Okay, let's discuss about different types of classifications. So there are three major types of classifications. One is binary classification, other one is multi-class classification, and the third one is multi-label classification. And it's simple to understand. Binary means two. Okay. Binary always means two. Either it is positive or negative, spam or no spam, something of that sort. Okay. Spam or no spam. So in binary classification task, the goal is to classify the input into two mutually exclusive categories. Yeah, do you know what is mutually exclusive categories? We already discussed this in the probability when we discussed Bayes' theorem. Mutually exclusive, exhaustive events, independent events, dependent events. Do you remember? Mutually exclusive events means if one event is happening, the other event will not happen. Okay, that is what mutually exclusive means. So the training data in such a situation is labeled in a binary format. That means um, the output of these kind of classifications is true or false, positive or negative, 0 or 1, spam or not spam, depending on the problem. Let's suppose this classifier is trying to distinguish truck and boat. So the output of this classifier will be boat or a truck. It will not be both truck and boat. Okay. So if you're feeding a new image, once this is trained, if you're feeding an image, it will say whether that is truck or boat. That is called as binary classification. In binary classification, only two values are possible as an output, not more than two. In multi-class means you can have uh, in multi-class classification. So for binary classification, the inputs are also two. Okay, the inputs will also be two classes, one of the two classes, and the output will also be one of the two classes. Okay, in multi-class classifier, you will have multiple classes, means multiple different types of objects. So the output of that particular multi-class classification can be anything. It can be from out of all the classes that are fed to it. It will be more than two basically. Minimum two, or even if it is more than two classes in the input data, it will handle that. In multi-class classification, on the other hand, at least two mutually exclusive events. So at least it should have two, where the goal is to predict to which class a given input belongs to. Okay. The difference between binary and multi-class classification is binary means only two classes will be there in the data. In multi-class means three classes will be there in the data. Class is nothing but each label. Truck is one kind of label, plane is one kind of class, boat is another class. So even if you have five different vehicles in the data, it can actually easily differentiate. I mean, it differentiates n number of classes as output. It can give output as truck, plane, boat, ship, whatever it is. It can give that output. Okay. It's just it's just the difference in the number of it's just the number of classes that it can handle, number of classifications that it can do. Spam or no spam is a binary classification, and uh, can this is an, I mean, if you're trying to name the animal, let's suppose if you're trying to differentiate cat, dog, lion, or whatever it is, like giraffe. If you're trying to differentiate multiple animals, that falls under multi-class classification. Binary means if you're trying to classify two items. Multi-class means if you're trying to classify more than two items. That is called as multi-class classification. Multi-label classification means in multi-label classification, in the same image, if you have multiple images, if you are able to classify, if you are able to predict everything in the input, so such kind of models are called as multi-label classification. In a single image, if you have multiple objects, you should be able to predict all the objects in that particular image. In the recent times, you might have seen, right, like there are cameras that have been installed on the highways, and they're trying to calculate number of lorries that have passed, number of bikes passed, number of cars passed. How are they doing that? They are doing that using multi-label classification. So they capture the video of that, and that this model which the model will be fed with the frames of that particular video, and then the model predicts the cars, bikes, and lorries, buses in that, and it actually summates the counts of or increments the counts of each of the objects. So that is what multi-level classification means. In multi-level classification, we try to predict zero or more classes. Okay, zero or more classes for each input example. Okay, zero or more class for in case there are no mutual exclusive, because the input example can have more than one label. There will not be there. I mean, there is no mutually exclusive because it can have anything. It can have two lorries, two boats, two aeroplanes. So it will just increment those counts. That is what multi-level classification means. It's simple. Binary means only two values are possible as an output. In multi-class, there could be n number of classes can come as an output. In multi-level, multiple classes can come together as an output. Okay, so this is these are different types of classifications. And now, a decision tree is one kind of algorithm that actually helps us to solve classification problems. Okay, it is easy to understand. So with this, I think we should be good to close. It's easy to understand as well. So decision trees, it looks like a tree. The best example for decision tree is that, like, this is like if else condition in any of the programming languages. If this condition is passed, go to if loop. If this condition didn't pass, go to else loop, something of that sort. So simple decision tree actually looks like this. A person wants to learn decision trees. If it is yes, check out here, stay here. If it is false, go check out an entertainment video. So this is a simple example for a decision tree. Okay, if your a decision is made, this is called as a node. Okay, this is trying to actually this is a condition. If this condition is true, you're going in one direction. If this condition is false, it is going in the other direction. But one thing to always remember is, in decision trees, everything that is coming up on the left is true case, and everything that is coming up on the right is a false case. Even if I don't write true or false in the decision trees, that means all the trues are coming on the left and all the falses are coming on the right side. So this is a simple decision tree. How does a decision tree actually looks like is, it will have a root node. The below the root node you will have an internal node. Internal node is a condition. Okay, internal node is a condition. So every internal node that you see is a condition. All leaf nodes are the classified items or the classes. Okay, all leaf floats are classes. That means the green color if you take an example, class 2 is no spam. Okay, class 2 is no spam and class 1 is spam. Okay, so based on different conditions that we do here, you have to decide whether that email is spam or not spam. Okay, all the leaf nodes are the classes that we want to derive. Okay, this is how the decision tree actually looks like. All right, so classification trees are of two types. Um, okay, so now this is the first machine learning classification algorithm that we are learning, and you have seen a simple decision tree. How does a decision tree looks like? And you also have seen the structure of the decision tree. Okay, now classification trees used for classification task where the output is a categorical variable. Okay, So if the leaf node is a categorical variable, such kind of trees are called as classification trees. Okay, spam or no spam, um, uh, dog or cat. If that is a categorical variable, if the leaf node is a categorical variable, we call that as classification trees. If the leaf node has continuous value, we call that as regression trees. So these are the outputs, right, that we are trying to predict. 350K, all that stuff are the outputs that we are trying to predict. Okay, so these are the outputs that we're trying to predict. If the leaf nodes are the outputs that we want to predict. If the leaf nodes has a continuous value or an integer value or a real value, we call that as regression trees. And if it has a categorical variable, something like spam node, something like, spam or no spam, if you or dog or no dog, dog or cat, if you're getting the output as a categorical variable, we call that as classification trees. So we will start with classification trees, and then we will actually learn regression trees later. Regression trees output has a continuous variable, so such kind of decision trees are called as regression trees. If the leaf nodes has categorical value, such kind of decision trees are called as classification trees. Now let's try to solve an example and understand the decision trees better. Now, given this particular data set, this is the data set that is given to us. Now we want to predict the risk of that particular. This is an insurance data based on the age and the car type. We are calculating the risk of insurance. Okay, insurance risk for that particular customer. So this is a simple data set. Whereas age and car type are independent variables, they don't have any relationship. Risk is a dependent attribute. We are trying to derive the risk attribute from the age and car type, which are you know uh, which are independent variables. Now I'll show you a simple decision tree here. So something like this. I would construct a random decision tree. I would say A is less than 20. Okay, I will start with this particular root node. A is less than 20, and then A is less than 20 means or less than or equal to 20. Okay, so such that what are values that comes towards this. So what all let's mark the customers 1, 2, 3, 4, 5, 6. So these are the customer IDs, let's say. Now less than or equal to 20 is true. If this is true, what are all the customers that come here? 2, 5 are the customers that fall here, right? And the rest of the customers 1, 3, 4, 5, 6 falls towards this. Now what I'll do is there are two customers, and what are the risk levels for this? Less than or equal to 20. For 2 the risk is high. For 5 the risk is high. So both of them are has risk high, right? Right, 5 and 2 has risk high. So this is concluded. So we don't have different kinds of customers. From this we can say that if the customer has A is less than or equal to 20, the risk is high. I would say the risk is high. Okay, and now here we can further break this, right? Finally, what we want to find out, the risk attribute. For that we just want to actually calculate this data. Okay, actually we have to split this into training and testing sets, but I'm not doing it. I'm just trying to show you. We will actually do that later, but now I am trying to show you how does a decision tree actually look like, and how do we construct a naive data set that I'm trying. Okay, now we have 1, 3, 4, 5, 6. Now we have 1, 3, 4, 5, 6. 1, 3, 4, 5, 6. 1, 3, 4, 5 is already done. So 6. So these are that are available. Now again, what can I do? Can I say this time I'll go with car type. Car type belong to. Now here I'll go to car type belongs to sports or vintage? Sports or vintage? This is my root node. If the car type belongs to sports or vintage, if this is S, this is no, true or false. What all points come here? So we have 25 sports. So that is true. So customer 1 falls here. And now this is the customer. This belongs to sports. So customer 3 falls this side. And what about this customer SUV? Doesn't belongs to sports or vintage. So that is no. So customer 4 falls here and customer 6 falls here. What are the risk levels for these two? So this is low, low, high and high, right? High and high. So now the decision tree looks like this. Simple decision tree looks like this. So I'm constructing it again. Age less than or equal to 20 is the root node. And here I would say this is the decision. This is risk is high. And now we have an internal node here that says car type belongs to sports or vintage. Sports or vintage. And now on the right side of this, it is low. The right side of it is high. Okay. Now on the training set, we have applied all the conditions and we were able to describe everything. Okay. Now let's suppose I'm getting a new data, something like this. The age is 30 and the car type is sports. Now if we want to predict the risk level of this particular customer, use this age less than or equal to 20. The age is 30. So this is false. I'll come here. Car type belongs to sports or vintage. It belongs to sport. True. So the risk level of this is low, right? So 30 age less than or equal to 20. 30 is not less than or equal to 20. So it is false. So we come in this direction. We will not go in this direction. And now we are checking. Now the next internal node says it is comparing the car type. Car type belongs to sports or vintage. So car type belongs to sports here, right? So it is true. So the risk level of this customer is low. So now let's say I have 20 and the car type is SUV. What is the risk level of this customer?
High.
Risk level is high because 20 is less than or equal to 20 is true. So the risk level is high. So now once we come up with this decision tree, we can actually predict the output. We can actually classify the customer as high risk or low risk. Now, is this the only possible decision tree that we can construct for this data? Age is less than or equal to 20 is what we have given. Can this not be age less than or equal to 25? Can this not be age less than or equal to 25? Or else, do we need to take only age less than or equal to 20? Don't we need to? I mean, is there any harm taking car type belongs to sports or vintage as the root? So there are n number of possibilities to construct the decision tree, right? So now out of all the possibilities that we have as a root node, we have to decide which is best, right? We have to decide which is best. So that is what we are going to learn now. So what is the best root node to get selected, and what are the parameters that we have to consider to actually choose that? Okay. The root node doesn't necessarily needs to be. What are the possible combinations for the A's? The possible combinations for the A's is A's can be less than or equal to 20. It doesn't necessarily needs to be 20. Okay. These are the points that are given to us, right? So these are the 5 points for us. We have 6 points. Where is the other point? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 20 sports, 25 sports, 20 vintage, 25 sports, 45 SUV, 20 sports. Oh, you have 25 sports. Okay, is there? 20 vintage is there. 25 sports is there.
25 sports is repeated 2 times.
Oh, it's repeated two twice. Sorry, maybe that's the reason. Okay, I have 5 points here. Okay, now let's consider this thing. Now we have these data points. Can I create root node as a is less than or equal to 26? I can do it as a is less than or equal to 27. I can do it as less than 40, 41, less than 45. I can do all these values, right? All of these values are possible. A's can take any of these values, right? You can take any value for this A's and you can create a root node. But technically, it would be a huge range, right? Yeah. So you need to restrict the values of the integers. I mean, if the internal node is a numerical value, there are infinite number of choices possible, right? A's can be anything out of these values from 20 to 45. It can be beyond 45, which but doesn't actually makes any sense. But the A's can take any value. There are infinite number of possibilities for the age, starting from 0 to 45, right? But that actually gives us an infinite set, but we don't want infinite set. What we try to make here is, if that is a numerical value, we pick only the values that occurred in the data. Okay, if that is a numerical value, we try to pick v as only the data points that is happening in the data. What are the values that are happening in this data? They are 20, 25, 20, 25 and 45. Okay, we try to take only these data points. Okay, anyways, between the pick only the values that occurred in the data. Anyways, if you see 45 would be redundant, right? Because if you take a is less than or equal to 45, every point will be less than or equal to 45. Okay, so again, it is not actually dividing the data at all. So there is no point taking 45. 45 is redundant. If you take 20 or 25, it is going to split the data into two parts, whereas 45 will not split the data into two parts. So 45 will become redundant. So when you are getting a numerical value, you are pruning that particular space for that age. A's can take any value. It can take A's can have infinite possibilities, but you want to prune it. So there are two ways to prune it. One is to take only the points that occurred in the data, and you make sure you remove all the redundant values. The edges will always be redundant. Okay, so what will be redundant? A is greater than or equal to 20 will be redundant, right? Gray is greater than or equal to 20 means it is again returning us all the data points again. It is not splitting the data. Okay, so these will be redundant things. So the potential internal limits could be based on ranges of thresholds. A is less than or equal to 20, A is less than 25, A is greater than 25, A is less than or equal to 45. So A is less than or equal to 45 is a redundant point because every point will be considered. Okay, this is redundant. I'm just telling you the possibilities, but again, we will calculate some parameters to make sure which is the best choice for the root node or the further internal nodes. Okay, so that is how you have to decide the values for the numerical data points. The first way is to choose the data points, choose the values that occurred in the data. And the second thing is pick only the midpoints between the actual values in the D-train. Okay. In the training set, choose only the midpoints. Okay. Pick only the midpoints between actual values in the D-train. Midpoints means, I would say, what are the values that we do have? 20, 25, 45, right? Choose a mid value in between these two, 20 plus 25 by 2. Okay, 20 plus 25 by 2. Choose a mid value in between these two, 25 plus 45 by 2. Okay, you can also choose the mid values between the points that occurred in the data, or pick the points that occurred in the data and make sure you remove the redundant points in the data. So these are the two ways to choose to choose the conditions for the numerical values. Okay. Now, if it is a categorical variable, let's see what are the possibilities. If it is a categorical variable, here in this case, what is the categorical variable? The categorical variables are sports, vintage, and SUV, right? Sports, vintage, and SUV. These are the things that we do have. Let me represent sports as SP, vintage as V, and SUV as SUV. What are the possible combinations for this? You can come up with this, right? Sports is one possible, vintage is one possible, SUV is one possible, and then SP and V is one possible. SP and SUV is one possibility, and then V and SUV is one possibility. SP, V, and SUV is one possibility. Okay, so these are the different possibilities that can be constructed. So car type belongs to sports, car type belongs to vintage, car type belongs to SUV. So these are the possibilities that we can derive. But if you carefully observe here, a few points will be redundant here. What are those few? So do you think these two are same? Do you think these two are same? Oh, those two will not be same. These two are opposite, right? These two are quite opposite. So you can say um, belongs to sports and vintage or doesn't belongs to SUV. You can write it that way, right? Hello.
Yes.
In
Yeah.
terms of capturing the data I'm talking about. So when you say uh, C belongs to sports and vintage, C belongs to SUV, C belongs to C belongs to. So this particular SPU and SUV, this does not capture any data. This becomes redundant, right? Because this will be part of everything. Okay, this will be part of everything. So if you just look at this data, if you this will not split this decision tree. Okay, when you use this as a node, it is not going to split the data into two parts. So every data will again come to this side. None of the points will be on this side. So we don't want such kind of conditions. We want the data in the data matrix to be splitted into two partitions. One side to be on the to be true and some points on the false side. Okay, as that is not happening with this, we are actually getting rid of it. Now talk about this. Okay, instead of saying C belongs to sports or vintage, you can say sports belongs to SUV, right? Because if you use this condition, the same will be covered here as well, right? In this also. So let's suppose let's take this particular diagram. Okay, so how do I explain this? So C belongs to sports and vintage is what we are saying. So we don't really need these three combinations. The reason being, these three combinations has covered all the values. That's what I mean to say. C belongs to SP and vintage. That means if you use this particular condition, what happens is um, you're giving two values. So for sports and vintage, both of them will be passed. That sports and vintage both will be passed. So, but instead of this, you if you give SUV, that will capture all the information. So what I mean to say is like SPV and SUV, these three will capture all the information, whereas this will not capture any additional information in the data set. Uh, oh, so what I'm trying to say is that these three is also capturing information with these three. So if you actually use this, C belongs to SP and V is already covered in C belongs to SP, C belongs to V, right? So if you give this as a condition, it's going to split the data into two parts. One is all of them coming towards S belongs to SUV, and all the other points that are coming towards, on the other side. So what is this doing? This is splitting all the car types other than SUV on one side and all the car types belonging to SUV on the other side, right? Even this is doing the same, right? If you say S belongs to SUV, this will also split all the cars belong to SUV on one side, all the cars that doesn't belongs to SUV on the other side, right? So that means the information that is captured by this condition is also been captured by this condition. So we don't need both of them, right? So it is simple. C belongs to SP and V vintage. What it is saying, it is moving all the cars that belongs to sports and vintage onto one side, and it is bringing the SUVs on the other side. But if you move this condition to the top, what it will do, it will bring SUVs and SP and vintage onto onto the other side, right. This is bringing, let's suppose, sports and vintage onto other side, SUVs on the other side. So this condition is doing this. What about S belongs to SUV? This is also doing the same, right? It is bringing SUVs on one side and sports and vintage on the other side. So both of these two conditions are doing the same action. So that's why I am saying these two are redundant. This become redundant, this become redundant, this become redundant. So only three possible conditions are sports, vintage, and SUV. So these three should be needed. Okay. So now we came up with the possibilities for categorical variables and numerical variables. Right, we came up with the possibilities of categorical variables and numerical variables. We were able to construct different possible combinations out of this age and car types. So for A's, what are the two ways to choose the internal nodes? The one way is to take only the points that are there in the data, or the other way is take the middle points between the data. Pick only the midpoints between the actual values in the data sets or in the training data set. For the categorical variables, construct all the possible combinations and capture or keep only the combinations that captures the whole data. For this sports, vintage, and SUV, we have constructed almost like 7 combinations. Out of that, most of them are redundant. Combinations of 2 and 3 are redundant. Only combinations of these 3 are redundant. So we will come up with all these internal nodes. As the second step, what we do now is we calculate the entropy of each condition. Now let me know, I'll let you know what does entropy actually means is that now using these conditions you can create n number of nodes, right? The first node can be a is less than or equal to 20, right? The first node, you don't really know what node has to be used as the root node. You know, this can be used as root node, this can be used as root node, this can be used as root node, but you have to decide now what has to be used as a root node. Okay, so for that what you have to do is you have to calculate the entropy of each node that we are using. So what does an entropy means and how do we calculate that is what we are going to see now. Okay. So before going there, what must 2 to the power 5 minus 1, which is 8 minus 1. Total number of partitions possible would be 8 minus 1 is 7. That's not a real. Now. Okay. Now let's understand what is how to calculate the possibilities of these things. Yeah, let me copy this data set. Create a new slide. Okay. Now, what I said, to decide on what needs to be used as the root node, we have to calculate the entropy. Entropy is nothing but it measures the amount of information residing in the data. How well that is capturing or splitting the information is what the entropy calculates. So less information means less entropy. More information means more entropy. So if the information gain, let me say about information gain. So what does information gain is like, let's take this example. If I'm taking this node age is less than or equal to 20. So this is one of the nodes, right? I will get 2 other nodes. This node will have what are the values that falls under this node? Again, I'm numbering this 1, 2, 3, 4, 5, 6. Okay. So what I'm getting here now is that do you want me to change this sports vintage sports? No. Okay. Now what are all the points that comes on this side now? The points that falls on this side is 2 and 5. And the others that fall here is 1, 3, 4, and 6. Okay. Now to calculate the entropy of this is the entropy of root, I would say. This is the entropy of level 1 and this is entropy of level 2. So from here to here, we have to calculate the information gain. To calculate the information gain, we have to calculate the entropy here, and we also have to calculate the entropy here. And then we have to subtract the entropy of this and this. Let's suppose this is entropy of A, entropy of B. Now, if you subtract the entropy at level A to entropy at level B, we get information gain. So the information gain has to be more. So such kind of node will be chosen as the root node. When the information gain is more, that means it is actually capturing more information in the data. That means it is actually splitting the data in the right way. So such kind of nodes has to be chosen. Okay. So how do we calculate the entropy? The entropy, the Shannon entropy, which measures the information gain is calculated by, of a particular data is calculated by minus sigma I is equal to 1 to k probability of I by log of probability of I. Okay, this value will be negative. That is why we are putting a negative value in before that. Okay, so that is how we calculated the entropy at different levels. So for this example, let's see how do we calculate the entropy, and then you will understand how to actually calculate the information gain out of the entropy. Okay. Um, Before that, let's take an example, and I'll show you calculating the entropy of this particular thing. Uh, let's suppose that is all. Let's suppose I have something like dataset. I have two classes. Okay, this is my class 1 and this is my class 2. Okay, now if I take the first diagram, every point that I have here, total number of points here is 7 points. Okay, I have 7 points and every point belongs to class 1. Now if I have to calculate the probability of high here, what is the probability of high? Probability of high is 7 by 7, which is equal to 1. I mean, probability of circles. Probability of cross is equal to 0 by 7, which is equal to 0. If I have to calculate the entropy, this will be minus 1 log 1, which is for class 1, plus 0 log 0. So that becomes, probability becomes 0, right? Log 1 is, what is log 1? 0, right? What is the value of log 1?
Not defined.
What is log 1?
Zero.
What is log 0?
Non-defined.
Undefined.
Undefined. Um, so let's suppose this is undefined and let's log 1 is 0. So let's mark the entropy as 0. So that means what I said, less entropy is less information and more entropy is more information. So the entropy here is 0. That means there is less information in this. That means everything belongs to only one class. So the entropy, the information here is less. There is no other thing. Even if any point is added to this, it is just, belongs to that class only, because there is no possibility of the other class. If you take the other example where I have 7 points belongs to this, and I do have another 7 points belonging to in another class. Okay, let's suppose I have 7 other points belongs to this particular class. Okay, 3 4 5 6. Okay, 6 points belongs to this particular class. Now if I want to calculate the probability here, probability of dot circles is equal to 6 by 12, which is 1 by 2. Probability of uh, probability of crosses is equal to 6 by 12, which is 1 by 2. If I have to calculate the entropy of this becomes minus 1 by 2 log 1 by 2 plus 1 by 2 log 1 by 2. So this is the probability for dots, circles, and this is the probability for cross. So this becomes minus log 1 by 2. So that is minus of minus log 2. So that becomes log 2, which is equal to 1. Let's suppose this is base 2. Log 2 to the base 2 is 1. So here the entropy is more. That means information is more in this. More entropy means more information. So the maximum possible value for the entropy is 1 and the minimum possible value for the entropy is 0. So 1 means more information and 0 means less information. Now this is how you calculate the probability and the information gain of the cases. So let's suppose, now let me show you how to calculate the probability for a particular case using this data. Okay, and then you will calculate the same way you will calculate the probability for all the classes, and you decide one class is the root node. Okay, let me take one example here. So what is the root node for that? Let's take the first condition, which is a is less than or equal to 20. Okay, I'm taking a is less than or equal to 20. Okay, now it is getting two nodes. The first node says what are the values that falls here? Again, 1, 2, 3, 4, 5, 6. Okay, now the first thing, the nodes that falls here is class high and class low. So the nodes is 2 and 5, right? 2 and 5. So class of this is high, class of this is high, 2 and 5. And the other side is we got how many values? 1, 3, 4 and 6. 1 is low, 3 is low, H is 4 is H, 6 is H. Now we got two lows and two highs on this side. Okay. Now if I have to calculate the entropy here, okay, if I calculate the entropy here, so this is true case, right? Or S case. This is true and this is false. And now let's take true case. In true case, what is the entropy of S or true? That means, let's suppose this is entropy of S and this is entropy of no. Okay, and then we calculate the whole entropy, which is weighted entropy. I'll also let you know how to calculate the weighted entropy, but let's calculate the entropy of true cases. Okay, so if it is true, we calculate entropy of high and low, right? The classes here is high and low. In the other example that we have seen, the classes are dot and cross. Here the classes are high and low. Okay, so now if I calculate the probability here of S, what is the probability of, you could probability of H is equal to 2 by 2, right? Which is 1. Probability of low is equal to 0 comma 2, that is 1. Here probability of H is equal to 2 by 4, that is 1 by 2. So 2 highs out of 4 records. Probability of low is equal to 2 by 4, that is equal to 1 by 2. So entropy of H of S is equal to minus of this is 0. 1 log 1 plus 0 into anything will be 0, right? 0 into undefined is 0. So this becomes 0. Now probability of no is equal to, I mean entropy of no is equal to minus 1 by 2 log 1 by 2 plus 1 by 2 log 1 by 2. Okay, so that becomes minus log 1 by 2, which is 1. Okay, so entropy of no is equal to 1, entropy of S is equal to, what is that? 0. Now this, we call this as the total entropy, we call this as split entropy. Okay, we have split the data, right? Now we call that as split entropy. Entropy of both of these together is called as split entropy. How do we calculate the split entropy? Now we know the individual entropies. Now we will calculate the split entropy. How do we calculate the split entropy? Split entropy is just nothing but the weighted entropy of these two. Okay, weighted entropy of these two is nothing but n for true, number of records for true by total number of records into entropy of true side or S plus number of records on false by total number of records into entropy of false. Entropy of our yes and no is nothing but true and false. This is entropy of true, this is entropy of false. Okay, this is called as weighted entropy. If we have the entropies equal on both the sides, we can just do the average of both the entropies, entropy 1 plus entropy 2 by 2. As the number of records are not equal, what we are doing is we are taking an weighted average, which is nothing but number of records on on one side by total number of records plus number of records on another side by total number of records. So number of records on this side is 2 records, right? 2 by total number of records is 6. 4 plus 2 is 6. On the on true side, we have 2 records into entropy of true is 0 plus number of records on the false side is 4 by total number of records is 6 into entropy of the false side, which is equal to 1. So this is coming down to be 2 by 6 into 0 is 0. 4 by 6 into 1 becomes 2 by 3 is the split entropy. So entropy of this is 2 by 3. Okay. So that is first thing that you have to understand. Now, here, now we have to calculate the probability here. How do we calculate the probability here? Here the whole data comes, right? This is the root node, so whole data will be there. So what is the probability of H here? Probability of H is equal to 4 by 6. Probability of low is equal to 2 by 6, right? Probability of H is equal to high is equal to 4 by 6. Probability of low is equal to. Now here you have to calculate the entropy minus 4 by 6 log 4 by 6 plus 2 by 6 log 2 by 6. Okay, here we have 6 records. Okay, we have total records here. Out of the 6 records, this whole data set will be here, and this data set is split into 2 records. So these 2 records will come here, and the rest 4 records goes here. Once that condition is, once the data is split, these 2 records will come here, right? These 2 records will come here, and the rest of the 4 records goes there. But on the top, we will have all the 4 records coming there only, right? So all these 4 records will be coming here. But initially at this phase, all the 6 records will be here. So as all 6 records are there, so 4 are high and 2 are low. So probability of high is 4 by 6, probability of low is 2 by 6. And calculate the entropy will be this value. So the value of this is 0. Let's suppose if I calculate the value here the value of minus 4 by 6 log 4 by 6 plus 2 by 6 log 2 by 6 is the entropy there is, if I calculate that, it becomes 0.275. Okay, this is the entropy at the root node, and the split entropy is, which is this, the calculated value of this. The split entropy is 2 by 3, right? Split entropy is 2 by 3 only. Split entropy is 2 by 3. Something like whatever it is, even if it is log 2 or log 1, if this is calculated as log 2, and if this is also calculated as log 2, this comes down to be 2 by 3 log 2, right? No. 4 by 6 into log 2 to the power of minus 1. Somewhere this is coming down to be, let's suppose this is coming down to be 0.202. Okay, the split entropy is coming down to be 0.202 if you are using base 2. And now if the information gain is nothing but information gain, this is what we are doing all these calculations to calculate this information gain. So information gain is nothing but h of d minus h of, this is split entropy, d of h minus h of s minus h of 0. So we are calculating difference of this entropies, which is nothing but, what does this value comes down to be? This comes down to be 0. The difference of those two values. Okay. The difference of those two values, which is so this is d of s d of no. So h of d is coming down to be 0.275 minus 0.202. So you will get something like 0.073, and this is the information gain. Okay, so we calculate the information gain for every such possibility. Okay, so this is one such information gain that we have calculated. So we calculate the information gain for every such possibility, and then whichever has the highest information gain, we actually go ahead and choose that as a root node. Understood? That means, so if you go back here, so now what are the possible combinations that we can derive? What are the possible nodes that we can derive out of this? So if you look at this, all the possible values that we can do this is, we already have discussed that. That is, that we should first come up, the first step is to come up with all the possible nodes, root nodes. So this is is less than or equal to 20 is the first one. And we have to calculate all the possible, I mean, what falls under the right and what falls under the left and the respective risks. Okay. And the second possibility is a is less than or equal to 25. Okay. This is one such possibility. The third possibility is, for numerical values, these are the two possibilities. And for categorical, it is car type belongs to sports. This is one, and then derive the outputs of this. And the fourth root node that is possible is car type belongs to SUV. Okay, and then derive both the nodes. And the fifth one is car type belongs to sports. Okay, car type belongs to sports, and we come up with those two values. Okay, so these are the possible root nodes that we can construct out of for this particular data, and we calculate the gain for all of this. Okay, for all these combinations, just now we have seen how do we calculate the gains. So we calculate the gains similarly for all of this. Okay, we calculate the gains for all these combinations. Let me put some values here so that you will understand how do we actually choose the actual training set or test set. Okay, let's suppose if I calculate the data here. Okay, let's suppose I'm getting this these values as the entropies, and then you can actually say it now. Let's say the information gain here is 0.5 for the case one, and the information gain for the second case is 0.155, and the information gain for the third one, I would say it as again 0.155, and the information gain for this is, I would say, 0.5, and the information gain for this is set to be 0.5, is set to be 1. So now look at the highest information gain. So that has to be taken as the root node. The node which has highest information gain will be taken as the root node. Okay, so now this would be the highest information gain. So the root node now will become car belongs to sports. Okay, so these are not exact calculations. I'm just giving you an example to decide on what to use as information node. So now we are using car belongs to sports as an root node, right? Now it divides the data into two parts. Okay, it divides the data into two parts, and now you have to choose the next, what is ideal risk with this. That would be better. Okay, now car belongs to sports has highest entropy, right? Now if you use this, if this is true, what all values that comes here? Car belongs to sports. So if I mark this 1, 2, 3, 4, 5, 6. Okay, so what all comes here? 1, 3, and 5 comes on this side, right? So this is low, 3 is low, 5 is high. Okay. And on the low side, this is true and this is false. On this side, what we are getting? We are getting 2 and 6. Both are high. Okay. So 2 and 6 both are high. So if it is false, if say that as risk as high. And now here, what is the other entropy which is high? After this, you have to choose one which has highest entropy. Okay. That is how you have to choose the internal node. After root node, to choose the internal node, you have to choose this way. So this is the leaf, this will become leaf node, right? So as this is ending up here, this will no more be a internal node. We will get this as a root node. So the root node now becomes high. So this is already derived, and the values for this is coming down to be so this is 2 and 6 will be coming out here, h and h. So on this side we get 1, 3, 4 and 5. So this 1 is L, 3 is L, 4 is H, and 5 is H, right? And now what is the other next highest entropy? Highest entropy is for 1 and 4, right? Highest entropy is for 1 and 4. Okay, so you can choose any one of these nodes. Either you can choose this or you can choose this. So if I choose A is less than or equal to 20, what happens? A is less than or equal to 20. True and false. What will fall on false side or true side? Less than or equal to 20. So 2 comes here, 5 comes here. So we don't have 2 anyways here. 2 already is concluded. Out of 1, 3, 4, 5, 1, 3, 4 and 5. So only 5 falls this side. 1, 3, 4 and 5. No, something is wrong. So I have written this wrong. 1 also falls this side, right? Car belongs to sports. Car belongs to sports. So how many sports are there? Only 3 sports are there. So
Fourth one has been
1, 2, 3. So only 3 is there. So 1, 3 and 5 are there. So only 1, 3, 5 falls this side. 2, 4 and 6. So 4 also comes this side. So this is high. So 2, 4, 6 are high. So this is high. This is done. So out of 1, 3, 4, out of 1, 3, 4, A is less than or equal to 20. What all comes this side and what all comes this side?
135.
1, 3, 5, yes. I'll just erase that. So 1, 3, 5 comes this side. So 1, 3, 5 comes this side. So 5 is high. So now if A is less than or equal to 20, what are all points stay this side? Out of 1, 3, 5, 1 goes this side, 2 comes this side, and 5 comes this side only, right? And 1 goes this side. Now 2 and 5 are high, right? 2 and 5 are high. So 2 and 5 are high. So this will become high. And 1 is low. Okay. So now this is the ideal decision tree. Out of many possible combinations that we have, this would be the ideal decision tree. This is how we construct the ideal decision trees. Okay, what we have done, the first thing is we have come up with all the possible conditions for numerical variable and categorical variable, and then we have calculated entropies for the root node and the split entropy. And then we calculated the information gain by subtracting the entropy of the root node minus entropy of the split criteria, split entropy. And once we got all the split entropies, we have choose the once we have calculated all the gains, we have chosen the node which has the highest gain. And then we have split the data. And once we have done that split, we have chosen the second highest entropy, and we use that as an internal node. And we keep on repeating the same till we separated all the classes successfully. Okay. So that is how the ideal tree will be constructed using decision trees. Okay. When you have more entropy, that means you have less information. H is equal to 1 means less information, and H is equal to 0 means low information. You already have seen that calculating entropy, right? Minus sigma for every I, PA log of PA. When you have only one class in your data points and you don't have any second class, you have got entropy as 0 because log 1 is equal to 0, right? So less entropy means less information. What is that? Less information means less entropy, more information means more entropy. So that is how you actually calculate the find out the ideal decision tree. Yeah, this is all about decision trees. Any questions? I think that's all for today.